Our universe is a vast and awe-inspiring place. It's filled with billions of galaxies, each containing billions of stars. But have you ever wondered where it all came from? How did this immense cosmic tapestry come to be? The prevailing scientific theory is the Big Bang. It suggests that our universe began from an extremely hot, dense state about 13.8 billion years ago. Imagine everything we see today compressed into a tiny point, smaller than an atom. From this point, the universe expanded outwards, cooling and evolving over eons into the cosmos we observe today. The journey from that initial point to the universe we know today is a fascinating tale of expansion, cooling, and the formation of matter. It's a story that scientists are still piecing together, but the evidence collected so far paints a picture of a universe born in a fiery explosion of energy and shaped by fundamental forces over billions of years. Let's journey back through time and explore the key events in this incredible story. Imagine a point infinitely small, containing all the energy of the universe. This point, called a singularity, is where our story begins. About 13.8 billion years ago, this singularity began to expand rapidly in a massive burst of energy. This expansion, known as the Big Bang, wasn't an explosion in the traditional sense. It was the rapid expansion of space itself, carrying matter and energy outward. Think of it like inflating a balloon. As you blow air in, the surface of the balloon expands, carrying everything on it further apart. The Big Bang is supported by a wealth of observational evidence, including the redshift of distant galaxies, the cosmic microwave background radiation, and the abundance of light elements in the universe. These pieces of evidence, like puzzle pieces, fit together to support the theory of a universe born from a single point. In the first fraction of a second after the Big Bang, something incredible happened. Cosmic inflation. The universe expanded at an unimaginable rate, much faster than the speed of light. Imagine a balloon suddenly inflating to an astronomical size in a tiny fraction of a second. This period of rapid expansion is crucial for understanding the universe's uniformity. It explains why the universe looks remarkably similar in all directions, even though regions of space are so far apart that they shouldn't have had time to interact with each other. Think of it like this. If you bake a cake and it rises unevenly, you know that the heat wasn't distributed properly. Similarly, if the early universe didn't expand uniformly, we would see variations in temperature and density across the cosmos. Cosmic inflation smoothed out any initial irregularities, creating a homogeneous universe. As the universe expanded and cooled, energy began to transform into matter. This transformation followed Einstein's famous equation E equals mach squared, which states that energy and matter are interchangeable. Initially, the universe was a chaotic soup of fundamental particles like quarks, electrons, and their antiparticles. As the universe cooled further, these particles began to combine, forming protons and neutrons, the building blocks of atoms. Imagine a dance floor filled with people moving rapidly and randomly. As the music slows down, people start pairing up, forming more stable structures. This is analogous to what happened in the early universe as particles combined to create the building blocks of matter. This process, known as baryogenesis, is still not fully understood by scientists. It's a key area of research as it holds the key to understanding why there's more matter than antimatter in the universe. Section 5. The first atoms, hydrogen and helium, light up the universe. Around 380,000 years after the Big Bang, the universe cooled enough for protons and neutrons to capture electrons, forming the first atoms. This era, known as recombination, marked a significant change in the universe. Before recombination, the universe was opaque, like a dense fog. The free electrons scattered light, preventing it from traveling freely. However, once atoms formed, the universe became transparent. Light could now travel unimpeded, and the universe became bathed in a faint glow. This faint glow, known as the cosmic microwave background radiation, is the oldest light we can observe in the universe. It's a faint echo of the Big Bang, providing us with a snapshot of the universe as it was just 380,000 years old. The first atoms to form were primarily hydrogen and helium, the simplest and most abundant elements in the universe. These elements would later become the fuel for the first stars. Section 6. The birth of stars, gravity's crucial role. After the formation of the first atoms, the universe was filled with vast clouds of hydrogen and helium gas. These clouds, denser in some regions due to tiny quantum fluctuations present since the Big Bang, began to collapse under their own gravity. As these gas clouds collapsed, they heated up, and their cores became incredibly dense and hot. When the temperature and pressure at the core reached a critical point, nuclear fusion began. Hydrogen atoms fused together, creating helium and releasing an immense amount of energy. This process, nuclear fusion, is what powers stars. The first stars were massive and short-lived, ending their lives in spectacular supernova explosions. These explosions seeded the surrounding space with heavier elements, paving the way for the formation of more diverse stars and planetary systems. Section 7. Galaxies, islands of stars in the vast cosmic ocean. Over billions of years, stars formed, clustered together and evolved, eventually forming vast structures called galaxies. Galaxies are immense collections of stars, gas, dust, and dark matter bound together by gravity. Our own galaxy, the Milky Way, is a barred spiral galaxy containing billions of stars, including our own Sun. It's just one of billions of galaxies in the observable universe. The formation and evolution of galaxies are complex processes influenced by various factors, including gravity, dark matter, and the energy released by stars and supernovae. As Section 8, Unveiling the Mysteries, the quest continues. The story of the universe's formation is a remarkable testament to the power of scientific inquiry. From a tiny point of unimaginable density and temperature, our universe has evolved into the complex and awe-inspiring cosmos we observe today. While scientists have made incredible strides in understanding the universe's origins, many mysteries remain. What caused the Big Bang? What is dark matter? And what role did it play in the universe's evolution? These are just a few of the questions that continue to drive cosmological research. As we continue to explore the universe and gather more data, we can expect to gain a deeper understanding of our cosmic origins. The quest to unravel the mysteries of the universe is a journey of discovery that will continue to inspire generations to come.